Welcome back to another rendition of Simulacra. I'm Bryson, and today is session 2 of building a decentralized application. So, in last session, we went over the requirements, non functional and functional, the core entities of the app, the API and the interface, and the data flow. And in this session, we will be actually drawing out the application using a wireframe and then going into some deep dives into where we can actually bolster our application and adhere to our non-functional requirements. So stay tuned for session 2 of building a decentralized application. Today we're doing high-level design. Hope you enjoy. Let's get into it. Alright, so welcome to session 2. We left off on data flow the last time, and that was coming off of our full system design architecture, where we have our primary goals, which will be to satisfy our functional and non-functional requirements. Then we have our requirements, core entities, API interface, data flow, high-level design, and deep dives. And so today, we're going to be going into high-level design. Now, when you want to think about high-level design, you want to think about, first of all, drawing the skeleton of your application very simply, and then we'll go into where we can actually scale the application, make more sense of our different functions and services, and so on. So first of all, we want to start with your client or your user. That's going to be your main core entity. And so we just want to take a box and make sure we put client over right here. So your client or your user will always go and hit an API gateway and load balancer before they interact with your application. This bolsters security and then also handles request and rate limits on request. And we'll get into that a little bit later. So cool. So pretty much every application is going to start like this, with a client going to an API gateway and then some sort of load balancer to balance requests that are coming in. So we're going to do this. So we're going to put one right here. All right, cool. So now we need to think about what sorts of things our application actually does. Well, we know that firstly, we know that our application takes address balances or community pool balances and can basically send the user back information regarding the balance of an address or a community pool. And so we need to make sure that we have that service taken care of. So let's come over here, it's right here, and we'll put the service that takes care of our address balances and the community pool info over here. And we know that we have to use a post request because we're posting an address or posting a transaction hash. And so we can make this a post request to our service right here. Cool. So we have that. And so what are some of the things that we want a balance address or an address to have in terms of info for our database that we're going to collect of address balances and any other user requests regarding information for the community pool? So we know that we're going to have for each address an ID, which is just the unique identifier for that address, the actual address ID for the blockchain, the address balance, and then the transaction hash ID for the pool or community pool info. So if our client is requesting this information, then we're going to need a database. And since our database is going to be pretty simple, we can use a Postgres database. Postgres databases are just relational databases. So think of tables, rows, and columns. When you want data that is pretty structured, you can use a Postgres database. But when you have things like maybe blob storage, or so that would be media or videos or audio, you want to use more of a non-relational database. But we're going to use Postgres. Postgres is extremely scalable, so we don't have to worry about any problems with reading heavily to the database. We know that our database is going to be very read heavy, and then our actual service for the address balances and the community pool information is going to be very write heavy. We'll get into how we can optimize that in a second. But so for our database, what kind of information does our database need to have? Well, we want to make sure that it has the same kind of things as our address pool, community pool service has over here. And so let's do that. Let's bring that over here. And we want to make sure that our database for our address balances and community pool information have all of the same tags as down here. We also want to make sure that the database can support up to 50 addresses per user so that our users with, a lot of different accounts for their crypto can be supported. Next, we have the actual service that deploys, funds, and withdraws from the community pool. We'll have that service, and we can put that service down here. And what exactly are we going to do to this service? Well, we're going to fund community pools, deploy community pools, and we can withdraw from community pools. And so all of those functions would be writing. We're writing to change the smart contract on the blockchain. So we know that we are posting a community pool when we want to deploy it. We can fund it also, and we can withdraw also, which are all post requests. So let's put our arrows from our load balancer. And next, we want to think about what kind of data our community pools are having. What happens during the withdrawal, the fund, and the deploy? Well, I wrote down some metadata and other attributes earlier, and so we can just copy and paste it down here. So for each deploy function, there needs to be a pool because we're deploying a community pool. And each pool will have a pool ID, the actual address ID of the community pool smart contract, the transaction hash ID of funding, withdrawing, and deploying the community pool, the pool balance, the available tokens that the pool can accept, any of the owners functions or rights, and then any metadata that has to do with the pool, whether that be the expiration date, fund limits, and the supported tokens, owners, etc. Next, we can say that the fund and the deploy will have the same parameters also. So we can put fund and deploy right here. And so we know that those will have the same parameters because they're doing the same thing, but just the opposite of each other. One, you are funding an account, and one, you're withdrawing from the account. So cool. Next, we need a database for the community pools. We need a database for the community pools. And so, because we already have our database over here, but we need another database for our community pools because it's going to be a lot of information and we want to keep them separate. Now, you could keep the address balance and the community pools database as one database, but there are problems that we will talk about later, such as stampeding and such, that it might be a good idea for us to keep two separate databases. We can always change later. We want to draw, and let me actually make all of this way smaller. Let's draw our database over on this area over here. So we have our community pools database. We're going to do a Postgres database because we don't have any non-relational data right now, any blob storage. We just have rows and columns. And so our communities pools database are going to have different parameters also. Right here, we can see there's going to be a pool, which is going to have a unique ID, an address ID, that's the actual blockchain address, the transaction hash ID, the pool balance, pool owners, etc. It's the same thing we went over. We want to make sure that our address balance service also has access to this database because our users are also posting the community pool addresses to get information on the community pool. So we want our service to have access to both. Now we can see that our service is able to hit our address balance database, and it's able to go to the community pools database to satisfy the user's request for information when they post an address or a transaction hash ID of the community pool or a crypto address. And so this is pretty simple in terms of what we want to do and what our app is going to do. But there are some places that we can now add a little bit more granularity to make sure that we're taking care of all of our non-functional requirements. Over here, we need to make sure that we're following the know your client policies and anti-money laundering policies. And so before our client, we're going to want to make sure that we have a service that allows our client to sign up or log in to our web application. And this is going to be a very write-heavy service because we're creating an account every time, or we're signing in or logging in every time that our client or user comes to our web application. So we're going to put that right here. And so even though that we have a API gateway and a load balancer, we still want to make sure that random users can't just overload our web application with requests. And so we want to have a rate limit to limit the amount of requests that any user can make on an ongoing basis. And then we also want to make sure that the application sends the user back a status code or an error code saying why their request was limited. And that'll be a 429 HTTP status code for too many requests. We can add rate limiters, and let's say that we'll have these additional headers when we add a rate limit. So we'll have a rate limit, and that's just going to be the limit ceiling for that request. It could be one request per 5 seconds. And then our remaining would be just the number of requests left in the current window, how many requests are left that the user can actually make, and then lastly, when that rate limit resets. So when that rate limit resets, you can have a timestamp and then a retry period, which could be 5 seconds. And so this is a great way to make sure that their users are not overloading your application with requests. So what's another way we can add security to our web application? Well, we can require users to input verification by email or number when they are signing in to our application. So this makes sure that we don't have any bots. We have real people with real numbers and emails that are using our application. So good. And then, so we need to make sure to add this 429 too many request status code when a user sends too many requests in too short a period to our application. So now we just handle a little bit of security and front end of knowing who is going onto our application, what their intentions are, and making sure that they cannot do some sort of stampeding or denial of service attack to our application. Now, where else can we bolster this application to make sure that we are handling our non-functional applications? We want to make sure that our users have a database so they're not constantly having to sign up and create accounts. Once they create an account, they have all their information, and so our application just can retrieve their information whenever they are requesting a request. So we're going to have a database for our users. We can put that up here. And this database is going to be a read-heavy database coming from the write-heavy client account creation service. And so we want to make sure that our service for creating an account is going to our database, and that also the client can read directly from the database when needed. So that's right there. We can have a database, and it can also be a Postgres because it's just going to be a relational database of columns and rows and pretty simple tables. But we want to make sure that we are adhering to Know Your Client. And basically, Know Your Client is making sure that each user that is on your application, and this is especially important in financial applications, and especially important in decentralized financial applications where anybody can have a crypto wallet, that we want to make sure that only good actors are on we want to make sure that only good actors are using our web application, no bad actors. And a good way to protect yourself as a developer is making sure that you have important and relevant information on your user. And so some of the parameters that make sure that your web application adheres to know your client policies are having your client's full name, date of birth, physical address, a phone number, and an ID or a license number that can actually be matched to that physical address. Really, the full name, date of birth, physical address, and ID license number are super important in know your client policies that basically make sure that you are interacting with a real person and a real person is using your application. Now that we have that, we've dealt with a lot of security of our app now. We have a rate limit. We require users to input a verification before they come on. We collect all of this information about them when they are creating an account. And then when they send too many requests, we send them a failure status code back. And so from the front end, we have some of the security aspects taken care of. Obviously, we can get way more in depth, but from a high level design, I think this is a good start. And so with our application, what do we need to think of next? Well, we want to have a way where there's not a stampede possibility when users are making requests to our application. A good way to, instead of using databases, a good way to handle stampeding is using caches. And so you can use a memory cache like Redis to basically hold information for a certain period of time, and it allows your application to be way more flexible and scalable so that your request doesn't always have to go to your database. We can go to the cache and check the cache for the information, and if the cache is not in the if the information is not in the cache, then we can go and check the database to fulfill the user request. And so one of the first places we can add a Redis cache is at this API gateway. We can add a Redis cache here. And this is a way we can help with also handling requests that come in and making sure that our API gateway and load balancers don't get overrun with requests. So any common requests from the client, we can just go and hit the Redis cache, see if we actually already have that request, and then send it back to them. And so a great way to think about caches, or one good way, is to think about bucket sizes and then the rate of tokens in that bucket that are decreasing as time goes on. So we can say that we have a rate of 1 token per 5 seconds, and then the bucket size of the actual Redis cache would be 100 tokens. The way that this flow in this process would go is that a request would come in, the gateway would fetch the token and the last refill time from Redis. We would then have a request, which would be a HM get, and that would be the client. You're getting the client and then the bucket tokens last refill. So next we're updating the counts based on the rate and the last refill. And then we're responding pass or fail based on if the tokens are greater than 0, and then we're updating the bucket status. And so this is another way, other than the rate limit down here, to make sure that our application is not getting overloaded with requests, and we have some sort of basically filter to make sure that users can make requests, but these requests aren't leading to the unscalability of our application. And as you can see, this is kind of a problem, because that means we're constantly reading and writing to this Redis instance, this cache. But it's not too bad of a problem, because we can use things like Redis Lua scripts. And basically, it's just a single instance of Redis, and it allows you to read and write atomic problems, and basically you read and write and you see those in one instance, and it takes care of that. So we can put that over here and remind ourselves to use a single Redis Lua script to drum up our Redis instance when we are creating this cache over here. There's another place that we would want to cache, and that is all the way over here with our address balance and our pull info service. Now remember, this is very write heavy. And so the flow of our application is that a client is using a address or transaction hash to get information about some sort of crypto address or community pool. And so we're constantly hitting this database, constantly hitting it, constantly hitting it, constantly hitting it. But there's a problem. What happens if a bunch of users at once want to get a certain address balance and they all hit this database at once? Well, in that case, so since we have this service constantly going to this address balance and wanting information back, we can create a cache to check if the data is present in the cache first or has been recently requested first, and then we can return it to the service, which returns it to the client before we actually even hit the database over here. So let's go up here and let's create another Redis cache down here. So let's go over here. We can create another one. So we want to make sure that our application checks the cache first, and if the data is present, it returns to the address balance or pool, address balance or community pool service, which returns the information back to the user. And if not, you have to query the database, and then you restore the result and the time to live and return. And so that ensures that if a user went and requested the balance or some information on a community pool 5 minutes ago, then it would just hit the Redis cache instead of going all the way to the database, which could be more computationally expensive and not efficient in the slightest. We have this cache over here for quick checking for requests. But we also have another problem. So what happens if a bunch of requests come in and we're hitting the Redis cache constantly, and we have an overrun cache, which is called a stampede? And so when we have a stampede and the cache fails and the database is overrun, we can proactively refresh the cache keys before the time to live to prevent popular keys from expiring and stampeding. And so we want to make sure that when we're setting up this Redis cache instance, that we make sure to structure it so that we proactively refresh cache keys before that TTL to prevent stampeding and expiring. And so to get a better sense of that, I'm going to go over here and draw out a little wireframe to show you exactly how caching works and how sharding also affects caching. So if we take this, let's post this over here. So right now, this is a pretty simplified version of our web application. You have your client, you have your application server, which hosts requests, you have your cache, and then you have your database. So this pretty simple structure shows our process for our application. And so there's really two main ways to cache. You can have our cache aside, or you can have our cache in line with the actual application server. When you're caching, you want to think, do I need to cache? And if you need to cache, think about, is this service very read heavy? Is it a read heavy workload? Are you constantly reading this database to send information back to your application server to send back to your client? If so, you might need a cache. Are those queries expensive? Do you have a high database CPU? Do you have high latency, or do you have a low latency requirements? Also, when you're caching, you want to make sure you identify the bottleneck, exactly what cache architecture you want to use, whether it's cache aside, the cache in the application server. You want to set an eviction policy. So, how long before your cache is flushed out? What is the TTL for your cache? And then you want to address all of the downsides like stampeding that we talked about earlier. This is also when you can get into sharding. And so as you can see, we have multiple instances of this cache. You can also have multiple instances of a database. But when you have multiple instances, it is called sharding. And when you are sharding, you want to think about what are you actually going to shard by and how are you going to distribute that data, which is called your cross-shard operations, and maintain consistency across shards. So shards, what to shard by? What to shard by means basically, say you have a application and you have users that are put in a database based on how many followers they have. So you have one cache for users that are 0 to a million followers. You have one cache for users that are 2 to 5 million. You have another cache of users that are 5 to 10 million. So that's what you're actually sharding by. So that means you're sharding by followers, and then the distribution is the distribution of those followers. And so as you can see, there's kind of a problem with this. What happens if this cache, what happens if this cache starts to be very popular? Say one of the followers is Drake, and your cache has a bunch of Drake hits. It's getting Drake hits all the time for users requesting information about Drake. Well, what you can do is so your cache doesn't become overloaded, you can actually store any hotkeys in a cache that's actually in your application server. So, for all, say, celebrity, this is called the celebrity effect, for all information that is very important or information that is constantly being searched for, you can put that right down here and make sure that every time my user is asking for a commonly searched for celebrity information, say a Drake, it hits this hotkey cache that has all of my hotkeys stored for very important or commonly requested information. And so that's a little bit about caching and sharding. Going back to our high level design, this is a good way to think about how to design any web application. You want to start with just the flow of your application, and the data flow really helps here. As you can see, user creates an account right here. The user can read balances of a posted address. The user can deploy community pools, fund community pools, and withdraw from community pools. And the user from here can see the recent transactions of that community pool with all community pool information going to the community pool database over here. Boom. And so we have our high level design. We went into some deep dives on where we can handle scalability, where we can add memory caches like Redis, where we can handle stampede possibilities. We can bolster our security by adding know your client and anti-money laundering processes. We can also handle security of our application by limiting the rate of request and putting some additional headers on requests so that our application is not being overrun with said requests. And so I think this is pretty good wireframing. This is pretty good high level design. And we went into some deep dives. This would definitely get you a lot of points in a system design interview if you were able to start with a simple idea and get all the way to this high level design with some deep dives. And so next session, we will start building our application. I'm going to go through the tech stack that I'm thinking about using. I want to make sure that this entire process is a very transparent application development process, and I want to take all of you on the journey with me. So, if you like this video, make sure to like and subscribe, support the channel, share with your friends. Comment below if you have any questions regarding system design. I think this is going to be a pretty interesting series, and we're going to learn a lot together. I'm definitely already learning a lot just by putting my thoughts into words and then presenting them to you all. So, thank you again. You've been watching another rendition, another video from Simulacra. I'm Bryson.